So, welcome grade 8 students. How are you? Good? Okay, so please go to www.cathomeschool.com. Okay, and click for the curriculum. Alright, then enter the password. Okay, then after that, click for science because science will be our lesson for today. Science. Click here. Okay. So first, we're going to talk about energy and work. What are energy and work? What does energy and work mean? So let's tackle and know about energy and work. So are you ready? Okay. So what does energy and work mean? So energy is a word which tends to be used a lot in everyday life. Though it is often used quite loosely, it does have very specific physical meaning. So energy is a measurement of the ability of something to do work. It is not a material substance. Energy can be stored and measured in many forms. Although we often hear people talking about energy consumption, energy is never really destroyed. It is just transferred from one form to another, doing work in the process. Some forms of energy are less useful to us than others. For example, low level heat energy. It is better to talk about the consumption or extraction of energy resources, for example, coal, oil, or wind, than consumptions of energy itself. A speeding bullet has a measurable amount of energy associated with it. This is known as kinetic energy. The bullet gained this energy because work has done on it by a charge of gunpowder, which lost some chemicals' potential energy in the process. Another example is a hot cup of coffee. A hot cup a hot cup of coffee has a measurable amount of thermal energy, which it acquired via work done by a microwave oven, which in turn took electrical energy from the electrical grid. So, in practice, whenever work is done to move energy from one form to another, there is always some loss to other forms of energy, such as heat and sound. For example, a traditional light bulb is only about 3% efficient at converting electrical energy to visible light, while a human being is about 25% efficient at converting chemical energy from food into work. Okay, so how do we measure energy and work? The standard unit used to measure energy and work done in physics is the joule, which has the symbol J in mechanics. 1 joule is the energy transfer when a force of 1 newton is applied to an object and moves it through a distance of 1 meter. Another unit of energy you may have come across is the calorie. The amount of energy in an item of food is often written in calories on the back of the packet. A typical 60-gram chocolate bar of example contains about 280 calories of energy. 1 calorie is the amount of energy required to raise 1 kilogram of water by 1 degree Celsius. This equal to 4,184 joules per calorie, so one chocolate bar has 1.17 million joules or 1.17 mj of stored energy. So that's a lot of joules. So how long do I have to push a heavy box around to burn off one chocolate bar? Suppose we're feeling guilty about eating a chocolate bar. We want to find how much exercise we need to do offset those extra 280 calories. So let's consider a simple form of exercise, pushing heavy bags around the room. So like this one, using a bathroom scale between ourselves and the box, we find that we can push with a force of 500 Newton. Meanwhile, we use stopwatch and measuring tape to measure our speed. This come out to be 0.25 meters per second. So how much work do we need to do to the box to burn out a candy bar? The definition of W is work. So work equals to F point um, squared triangle X. So the work need to burn the energy in the candy bar is E equals to 80 cal point 4,884 joule equals to 1.70 million. So the distance we need to move the box through is this equation. Remember, however, that our bodies are about 25% efficient at transferring stored energy from food into work. The actual energy will offset is then 4 times as high as the work done to the box. So we only need to push the box through a distance of 585 meters, which is still over 5 football fields long. So as you can see, here is the equation. Alright. We also have here exercise. Okay, but before we go further, I have this video here about the introduction of work and energy.
Welcome back. I'm now going to introduce you to the concepts of work and energy. And these are two words that are, I'm sure you use in your everyday life already, and you have some notion of what they mean, but maybe just not in the physics context, although they're not completely unrelated. So work, you know what work is. Work is when you do something. You go to work, you make a living. In physics, work is, and I'm going to use a lot of words, and they actually end up being kind of circular in their definitions. But I think when we start doing the math, you'll start to get at least a slightly more intuitive notion of what they all are. So work is energy transferred by a force. So I'll write that down. Energy transferred. And I got this from Wikipedia because I wanted a good, I guess, relatively intuitive definition. Energy transferred by a force. That makes reasonable sense to me, but then you're wondering, well, I know what a force is. Force is mass times acceleration, but what is energy? And then I looked up energy in Wikipedia, and I found this, well, entertaining, but it also, I think, tells you something, that these are just concepts that we use to, I guess, work with what we perceive as motion and force and work and all of these types of things, but they really aren't independent notions. They're related. So Wikipedia defines energy as the ability to do work. So they kind of use each other to define each other, ability to do work. Which is, frankly, as good of a definition as I could find. And so with just the words, these kind of don't give you much information. So what I'm going to do is move on to the equations, and this will give you a more quantitative feel of what these words mean. So the definition of work in mechanics: work is equal to force times distance. So let's say that I have a block, and let me do it in a different color just because this yellow might be getting tedious. And I apply a force of, let's say I apply a force of 10 newtons, and I move that block by applying a force of 10 newtons. I move that block, let's say I move it, 7 meters. 7 meters. So the work that I applied to that block, or the energy that I transferred to that block, the work is equal to the force, which is 10 newtons, times the distance, times 7 meters. And that it would equal 70 10 times 7. Newton meters. So Newton meters is one I guess, way of describing work. And this is also defined as 1 joule. And I'll do another presentation on all of the things that the joule did. But joule is the unit of work, and it's also the unit of energy. And they're kind of transferable, because as we look at the definitions that Wikipedia gave us, work is energy transferred by a force, and energy is the ability to do work. So I'll leave this relatively circular definition alone now. But we'll use this definition, which I think helps us a little bit more, to understand the types of work we can do, and then what kind of energy we actually are transferring to an object when we do that type of work. So let me do some examples. Let's say I have a block. I have a block of mass m. I have a block of mass m, and it starts at rest. And then I apply force, let's say I apply a force F for a distance of, I think you can guess what the distance I'm going to apply it is, for a distance of d. So I'm pushing on this block with a force of F for a distance of d. And what I want to figure out is, well, we know what the work is, by definition, work is equal to this force times this distance that I'm applying the block, that I'm pushing the block. But what is the velocity going to be of this block over here, right? It's going to be something somewhat faster, right? Because force isn't, and I'm assuming that this is frictionless on here, so force isn't just moving the block with a constant velocity. Force is equal to mass times acceleration, so I'm actually going to be accelerating the block. So even though it's stationary here, by the time we get to this point over here, that block is going to have some velocity. We don't know what it is because we're using all variables. We're not using numbers. But let's figure out what it is in terms of v. So if you remember your kinematics equations, and if you don't, you might want to go back, or if you've never seen the videos, there's a whole set of videos on projectile motion and kinematics. But we figured out that when we're accelerating an object over a distance, that the final velocity, change colors just for variety, the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the distance. And we proved this back then, so I won't redo it now. But in this situation, what's the initial velocity? Well, the initial velocity was 0, right? So the equation becomes vf squared is equal to 2 times the acceleration times the distance. And then we could rewrite the acceleration in terms of what? The force and the mass, right? So what is the acceleration? Well, F equals ma, or acceleration is equal to force divided by mass. So we get vf squared is equal to 2 times the force divided by the mass times the distance. And then we could take the square root of both sides if we want. We get the final velocity of this block at this point is going to be equal to the square root of 2 times force times distance divided by mass. And so that's how we could figure it out. And there's something interesting going on here. There's something interesting in what we did just now. Do you see something that looks a little bit like work? Well, sure. You have this force times distance expression right here. Force times distance right here. So let's write another equation. If we know the given amount of velocity something has, if we can figure out how much work needed to be put into the system to get to that velocity, well, we can just replace force times distance with work, right? Because work is equal to force times distance. So let's go straight from this equation because we don't have to re-square it. So we get vf squared is equal to 2 times force times distance. That's work. Took that definition right here. 2 times work divided by the mass. Let's multiply both sides of this equation times the mass. So you get mass times the velocity. And we don't have to write, I'm going to get rid of this f because we know that we started at rest and that the velocity is going to be, let's just call it v. So m times v squared is equal to 2 times the work, or let's divide both sides by 2, or that the work is equal to mv squared over 2. Just divided both sides by 2. And of course the unit here is joules. So this is interesting. Now, if I know the velocity of an object, I can figure out, using this formula, which hopefully wasn't too complicated to derive, I can figure out how much work was imputed into that object to get it to that velocity. And this, by definition, is called kinetic energy. This is kinetic energy. And once again, the definition that Wikipedia gives us is the energy due to motion, or the work needed to accelerate from an object from being stationary to its current velocity. And I'm actually almost out of time, but what I will do is I will leave you with this formula, that kinetic energy is mass times velocity squared divided by 2, or 1/2 mv squared. It's a very common formula. And I'll leave you that, and that is one form of energy. And I'll leave you with that idea. And in the next video, I will show you another form of energy. And then I will introduce you to the law of conservation of energy, and that's where things become useful, because you can see how one form of energy...
Okay. I have this another video, a part 2 about work and energy. Wait, this is another video about work and energy. Let's all watch this.
Welcome back. In the last video, I showed you, or hopefully I did show you, that if I apply a force of F to an initially stationary object with mass m, and I apply that force for a distance d, that force times distance, the force times the distance that I'm pushing the object, is equal to 1/2 mv squared, where m is the mass of the object, and v is the velocity of the object after pushing it for a distance of d. And we defined in that last video, we just said that this is work. Force times distance, by definition, is work. And 1/2 mv squared, I said this is called kinetic energy. Kinetic energy. And so by definition, kinetic energy is the amount of work, and I mean this is the definition right here, it's the amount of work you need to put into an object or apply to an object to get it from rest to its current velocity. So its velocity over here. So let's just say I looked at an object here with mass m and it was moving with the velocity v. I would say, well, this has a kinetic energy of 1/2 mv squared. And if the numbers are confusing you, let's say the mass was, I don't know, let's say this was a 5 kilogram object and it's moving at 7 meters per second. So I would say the kinetic energy of this object is going to be 1/2 times the mass times 5 times 7 squared times velocity squared times 49. So let's see, 1/2 times 49, that's a little under 25. So it'll be approximately 125 Newton meters, which is approximately, and a Newton meter is just a joule, 125 joules. So this is if we actually put numbers in. And so when we immediately know this, even if we didn't know what happened, how did this object get to this speed? Let's say we didn't know that, someone else had applied a force of m for a distance of d to this object. Just by calculating its kinetic energy as 125 joules, we immediately know that that's the amount of work that was necessary. And we don't know if this is exactly how this object got to this velocity, but we know that that is the amount of work that was necessary to accelerate the object to this velocity of 7 meters per second. So let's give another example. And instead of this time just pushing something in a horizontal direction and accelerating it, I'm going to show you an example. We're going to push something up, but its velocity really isn't going to change. Let's say I have a different situation. And we're on this planet, we're not in deep space. And I have a mass of m. And I were to apply a force. So let's say the force that I apply is equal to mass times the acceleration of gravity. Mass times, let's just call that gravity, right? 9.8 meters per second squared. And I were to apply this force for a distance of d, upwards, right? Or instead of d, let's say h. H for height, right? So in this case, the force times the distance is equal to, well, the force is mass times the acceleration of gravity, right? And remember, I'm pushing with the acceleration of gravity upwards, while the acceleration of gravity is pulling downwards. So let's say, so the force is mass times gravity, and I'm applying that for a distance of h, right? D is h, so the force is this. This is the force. And then the distance I'm applying is going to be h. And what's interesting is, and this is a bit of, if you want to think of an exact situation, imagine an elevator that is already moving, because you would actually have to apply a force slightly larger than the acceleration of gravity just to get the object moving. But let's say that the object is already at constant velocity. Let's say it's an elevator. And it is just going up with a constant velocity, and let's say the mass of the elevator is, 10 kilograms. 10 kilograms. And it moves up with a constant velocity. It moves up, it moves up 100 meters. So we know that the work done by whatever was pulling on this elevator, it probably was the tension in this wire that was pulling up on the elevator. But we know that the work done is the force necessary to pull up on it. Well, that's just going to be the force of gravity. So we're assuming that the elevator is not accelerating, right? Because if the elevator was accelerating upwards, then the force applied to it would be more than the force of gravity. And if the elevator was accelerating downwards, or if it was slowing down upwards, then the force being applied would be less than the acceleration of gravity. But since the elevator is at a constant velocity moving up, we know that the force pulling upwards is completely equal to the force pulling downwards, right? No net force, because gravity and this force are at the same level, so there's no change in velocity. I think I said that 2 times. So we know that this upward force is equal to the force of gravity. So this is, at least in magnitude, in the opposite direction. So this is mg. So what's m? M is 10 kilograms times the acceleration of gravity. Let's say that's 9.8 meters per second squared. I'm not writing the units here, but we're all assuming kilograms and meters per second squared. And we're moving that for a distance of 100 meters. 100 meters. So how much work was put into this elevator, or into this object, it doesn't have to be an elevator, by whatever force that was essentially pushing up on it or pulling up on it. And so let's see, this would be 98 times 100, so it's 9,800 Newton meters, or 9,800 joules. And when we're at the top of, after we've moved up 100 meters, notice there's no change in velocity. So the question is, where did all that work get put into the object? And the answer here is that the work got transferred to something called potential energy. So, and potential energy is defined as, well, gravitational potential energy. We'll work with other types of potential energy later with springs and things. Potential energy is defined as mass times the force of gravity times the height that the object is at. And why is this called potential energy? Because at this point, the energy work had to be put into the object to get it to this, in the case of gravitational potential energy, work had to be put into the object to get it to this height. But the object now, it's not moving or anything, so it doesn't have any kinetic energy, but it now has a lot of potential to do work. And what do I mean that? What do I mean by potential to do work? Well, after I move an object up 100 meters into the air, what's its potential to do work? Well, I could just let go of it and have no outside force other than gravity. Gravity will still be there. And because of gravity, the object will come down and be at a very, very fast velocity when it lands. And, maybe I could apply this to some machine or something, and this thing could do work. And if that's a little confusing, let me give you an example. It all works together with our... So let's say I have an object that is, a 1 kilogram object we're on Earth, and let's say that it is 10 meters above the ground. 10 meters above the ground. So we know that its potential energy is equal to mass times gravitational acceleration times height. So mass is 1, gravitational acceleration, let's just say gravitational acceleration is 10 meters per second squared, times 10 meters per second squared, times 10 meters, which is the height. So it's approximately equal to 100 Newton meters, which is the same thing as 100 joules. Fair enough. And what did we know about this? We know that it would take about 100, or exactly 100 joules of work to get this object from the ground to this point up here. Now, what we can do now is use our traditional kinematics formulas to figure out, well, if I just let this object go, how fast will it be when it hits the ground? And we could do that, but what I'll show you is even a faster way. This is where all of the work and energy really becomes useful. We have something called the law of conservation of energy, is that energy cannot be created or destroyed. It just gets transferred from one form to another. And there are some minor caveats to that, but for our purposes, we'll just stick with that. So in the situation where I just take the object and I let go up here it has a ton of potential energy, right? And by the time it's down here, it has no potential energy because the height becomes 0, right? What's its potential energy? So here, potential energy is equal to 100. And here, potential energy is equal to 0. And so the natural question is, I just told you the law of conservation of energy, but if you look at this example, all the potential energy just disappeared. And it looks like I'm running out of time, but what I'll show you in the next video is that that potential energy gets converted into another type of energy. And I think you might be able to guess what type that is, because this object is going to be moving really fast right before it hits the ground. I'll see you in the next video.
Okay, so that will be our that will be about work and energy. But please study our lesson, because on our next video I will give you an activity about work and energy. Okay, okay, that's all for today.